Special integral form, \int ex f(x plus fx) \dx. Okay, so let's move on to a really useful technique in integration. Now, in the sections we've covered so far, you've learned about integration by parts, a very powerful method for tackling integrals. However, as you've probably noticed while practicing, integration by parts can sometimes be quite lengthy, involving several steps and potentially messy algebra. It's a solid method, but not always the most efficient. What we're going to look at now is a special case, a sort of shortcut identity that will allow us to solve certain integrals much faster. We're not abandoning integration by parts, it's still a valuable tool, but this will add to your toolkit. This shortcut applies to integrals that have a very specific form. When you see an exponential function, e to the power of x, multiplied by a combination of another function and its derivative. If the integral you're facing matches this pattern, you can evaluate it almost instantly. We'll be learning exactly how to recognize this pattern and apply the shortcut in the following slides. So, pay close attention to the specific form we're about to discuss. Understanding the identity. Now, there's a particular pattern that appears in calculus where we have an exponential function, specifically e to the x, multiplied by the sum of a function, which we're calling f of x, and its derivative, which we denote as f prime of x. Essentially, when you encounter an integral of this form, there's a beautiful, clean result. And that result is stated right here. The integral of e to the x, multiplied by the quantity f of x plus f prime of x, with respect to dx, is equal to e to the x multiplied by f of x, plus the constant of integration, c. Let me say that again, just to make sure it's clear. The integral of e to the x times f of x plus f prime of x, with respect to dx, simplifies to e to the x times f of x plus c. In simpler terms, if you spot this specific pattern, e to the x, multiplied by something in brackets that contains a function and its derivative, you don't need to go through the full integration by parts process. The integral is simply e to the x times the original function, f of x, plus our usual constant of integration. Okay, so let's move on to slide 2. As we discussed on the previous slide, integration by parts can sometimes be a bit lengthy. This slide introduces a special case, a shortcut, if you will, that can significantly simplify things. We'll see why this works on the next slide, where we'll actually derive this formula using integration by parts. But for now, just understand the pattern and what the result will be when you see it. This will save you a lot of time and effort. Derivation of the formula. Okay, so far we've seen that the integral of e to the x times the quantity f of x plus f prime of x is simply e to the x times f of x plus a constant. It seems almost too good to be true, right? That's why, on this slide, we're going to prove why this shortcut works. We'll do this by starting with something you already know, integration by parts. Remember the integration by parts formula. It states that the integral of u with respect to dv is equal to uv minus the integral of v du. We're going to use this as our foundation. Now let's begin the derivation. Step 1, split the integral. We have the integral of e to the x times the quantity f of x plus f prime of x with respect to dx. We'll start by distributing the e to the x across the bracket. This gives us the integral of e to the x times f of the x, plus the integral of e to the x times f prime of x, both with respect to dx. Essentially, we've just broken down one integral into two simpler ones. Step 2, apply integration by parts to the first term. Let's focus on the integral of e to the x times f of x with respect to dx. To apply integration by parts, we need to carefully choose what parts of the integrand will be our u and our dv. Let's choose u to be equal to f of x. This means that the derivative of u, which is du, will be f prime of x dx. And we'll choose dv to be e to the x dx. This means that v, the integral of dv, will be e to the x. Now we can plug these choices into our integration by parts formula. We have the integral of u dv, which is the integral of f of x times e to the x dx. According to the formula, this is equal to uv, which is f of x times e to the x, minus the integral of v du, which is the integral of e to the x times f prime of x dx. So, we've successfully applied integration by parts to the first part of our original integral. In the next slide, we'll continue substituting and simplifying to see how everything cancels out and leads us to our shortcut formula. Remember, we're not just memorizing a rule, we're understanding why it works. Derivation of the formula, continued. Okay, so we've been working through the derivation of this handy integral shortcut, and now we're on to step 3. Remember, in the previous slide, we used integration by parts to break down the integral. Now, step 3. Substitute this result back into the original equation. What this means is, we're going to take the result we got from applying integration by parts to the first part of our split integral, that is, integral of e to the power of x times f of x, and plug it right back into where it originally was. Let me show you what that looks like. We started with the integral of e to the power of x times the quantity f of x plus f prime of x with respect to dx. We split that into two integrals, and then we tackled the first integral of e to the power of x dollar times f, x dollar. We found that this equals f, x dollar times e dollar to the power of x dollar minus the integral of e dollar to the power of x dollar times f dollar prime of x dollar. Now, we're substituting that back in. So, our equation becomes the integral of e to the power of x times f of x plus the integral of e to the power of x times f prime of x equals, and now we substitute, open bracket, f of x times e to the power of x minus the integral of e to the power of x times f prime of x, close bracket, plus the integral of e to the power of x times f prime of x. Now let's move on to step 4, simplify. If you look closely, you'll notice something beautiful happens. We have a negative integral of e to the power of x times f prime of x, and a positive integral of e to the power of x times f prime of x. These two terms perfectly cancel each other out. They are additive inverses. So, what's left? We're left with just the integral of e to the power of x times f of x plus f prime of x equals e to the power of x times f of x plus the constant of integration, c. And that, my friends, is it. This derivation proves that we do not need to perform the full integration by parts process every time we encounter this specific form. It's a shortcut, and now we understand why it works. This will save us a lot of time and effort when we're solving integrals that fit this pattern. In the next slide, we'll look at exactly how to apply this shortcut step by step. How to apply the identity step by step. Okay, so now that we've seen why this special integral form works, we derived it using integration by parts on the previous slides, let's talk about how to actually use it to solve problems. This slide outlines a step-by-step approach, and it's really important to follow these steps systematically. First, identify the exponential. This might seem obvious, but it's crucial. We need to make absolutely sure that the integral we're trying to solve contains the factor e to the power of x. Remember, this shortcut only works when e to the power of x is part of the integrand. Next, isolate the bracket. Once you've confirmed the presence of e to the power of x, focus on what's being multiplied by it. That is, identify the expression inside the brackets. This bracketed expression is where the key to applying our shortcut lies. Now comes the slightly more involved part, test for derivative. This is where we confirm if the integral actually fits the pattern our shortcut requires. We need to check if one part of the expression inside the bracket is the derivative of the other part. Let's break that down further. First, identify f of x. Choose one of the terms inside the bracket and designate it as f of x. It doesn't matter which one you pick initially, but one will work and the other won't, so we need to test. Then, calculate f prime of x. Find the derivative of the function you just chose as f of x. Finally, verify if the bracket is exactly f of x plus f prime of x. This is the critical step. Does the expression inside the bracket perfectly match the sum of your chosen function and its derivative? If it does, you're good to go. If not, this shortcut won't work, and you'll need to use a different integration technique. And finally, apply the shortcut. If you've successfully verified that the integral is in the correct form, then the solution is simply e to the power of x, multiplied by your original function f of x, plus the constant of integration, c. So, the integral evaluates to e to the power of x times f of x plus c. We'll see this in action on the next few slides with some worked examples, but mastering these steps will allow you to quickly and efficiently solve integrals of this special form. Remember, it's all about recognizing the pattern and verifying that it fits before applying the shortcut. Worked examples. Okay, let's move on to our first worked example. As we discussed in the previous slides, we're looking for integrals that fit the form integral of e to the power of x, multiplied by the sum of a function and its derivative. Here, we're asked to evaluate the integral of e to the power of x, multiplied by the quantity sine x plus cosine x, with respect to dx. Now, let's follow the steps we outlined on slide 5. Step 1. Identify the functions. We can clearly see that our integrand, that's the function we're integrating, is e to the power of x multiplied by the expression sine x plus cosine x. To apply our shortcut, we need to identify what will be our f of x. Let's choose f of x to be sine x. Step 2. Find the derivative. We need to find the derivative of our chosen f of x, which is sine x. Recall from your differentiation rules that the derivative of sine x is cosine x. Therefore, f prime of x, which represents the derivative of f of x, is cosine x. Step 3. Verify the form. Now, the crucial step, we need to check if our integral actually matches the form we need for the shortcut. We have e to the power of x multiplied by the bracket containing f of x, which is sine x, plus f prime of x, which is cosine x. This perfectly matches the form e to the power of x multiplied by the quantity f of x plus f prime of x. Step 4. Final result. Because we've verified the form, we can directly apply our identity. The integral of e to the power of x multiplied by sine x plus cosine x is simply e to the power of x multiplied by f of x, which is sine x, plus our constant of integration, c. So, the final answer is e to the power of x sine x plus c. And that's it. We've successfully evaluated the integral using our shortcut. Remember, this method is much faster than using integration by parts in this case. In the next example, we'll see how to handle integrals that require a little bit of algebraic manipulation before we can apply the identity. Worked examples continued. Okay, let's move on to our second worked example. This one demonstrates a slightly different scenario where we need to do a little bit of algebraic thinking before applying our shortcut. Here we have the integral of e to the power of x, multiplied by the quantity 1 over x minus 1 over x squared, with respect to dx. Remember from the previous slides, our goal is to see if we can rewrite this integral into the form integral of e to the power of x times the sum of a function and its derivative. Step 1. Identify the functions. The expression that's being multiplied by e to the power of x is 1 over x minus 1 over x squared. Now, we need to strategically choose what we'll call our function, f of x. Let's choose f of x to be 1 over x. Step 2. Find the derivative. Now, let's find the derivative of our chosen function, f of x. So, we need to find the derivative of 1 over x. Remember that 1 over x can be written as x to the power of negative 1. Applying the power rule, which states that the derivative of x to the power of n is n times x to the power of n minus 1, we get negative 1 times x to the power of negative 2. This simplifies to negative 1 over x squared. So f prime of x, the derivative of f of x, is negative 1 over x squared. Step 3. Verify the form. Now, the crucial step. Let's check if our choice of f of x works. We need to see if the expression inside the brackets matches the form f of x plus f prime of x. We have 1 over x plus negative 1 over x squared, which is exactly the same as 1 over x minus 1 over x squared, the original expression inside the brackets. So, we've successfully verified that our integral fits the required form. Step 4. Final result. Excellent. Now we can confidently apply our shortcut formula. The integral of e to the power of x times the quantity f of x plus f prime of x is simply e to the power of x times f of x, plus the constant of integration. See, since f of x is 1 over x, Our final answer is e to the power of x times 1 over x plus c, which we can write more neatly as e to the power of x over x plus c. And that's it. This example shows that sometimes you might need to do a little bit of manipulation or strategic function selection, but once you get the integral into the correct form, the shortcut makes the integration very straightforward. Remember, we'll be looking at common mistakes in the next slide, so pay attention to those to avoid any pitfalls. Common mistakes to avoid. First, and this is a really common one, is getting the sign wrong. Many students will instinctively try to apply our shortcut, the integral of e to the x times f of x plus f prime of x, to integrals where there's a subtraction sign instead of an addition. So, something like the integral of e to the x times f of x minus f prime of x. Remember, this identity only works when you have a sum inside the brackets. If you see a minus sign, the formula won't give you the correct answer, and you'll need to use a different integration technique, like standard integration by parts. Next, be careful with selecting your f of x always, and I mean always. Double-check that the function you choose as f of x actually gives you the other term when you take its derivative. In other words, if you pick a function f of x, make sure that its derivative, f prime of x, is the other function inside the brackets. If you pick the wrong function, the identity simply won't apply, and you'll get an incorrect result. It's a quick check, but a crucial one. Finally, and this is a more conceptual mistake, don't forget the importance of the e to the x. This shortcut works specifically because the derivative of e to the x is itself. E to the x, this is a unique property of the natural exponential function. You can't use this shortcut directly with other exponential bases, like 2 to the x or 10 to the x, without first adjusting for the natural logarithm constant. If you were to encounter those, you'd need to incorporate a natural log term into your solution. Okay, let's move on to slide 8, where we discuss some common mistakes students make when applying this special integral form. It's good to know these pitfalls before you start solving problems so you can avoid them. So, keep these 3 points in mind as you practice, and you'll be well on your way to mastering this special integral form. Now, let's move on to the final slide where we'll recap the key takeaways. Key takeaways. First, and most importantly, remember the identity itself. The integral of e to the power of x, multiplied by the quantity f of x plus the derivative of f of x with respect to x, all with respect to x, is equal to e to the power of x multiplied by f of x, plus the constant of integration. See, so, we write that as integral of e to the power of x times f of x plus f prime of x dx equals e to the power of x times f of x plus c. Make sure you have that memorized, as it's the core of this technique. Now, why is this identity so useful? It provides efficiency. As we saw earlier, without this shortcut, we'd have to go through the full process of integration by parts, which can be quite lengthy and prone to algebraic errors. This form allows us to jump directly to the answer, saving us time and effort. Remember, we derived this formula using integration by parts on slides 3 and 4, so you understand where it comes from. However, it's crucial to remember the requirement for this shortcut to work. The integrand, that's the function you're integrating, must be a product of e to the power of x and the sum of a function and its derivative. If it doesn't fit that exact pattern, you can't use this identity. You'll need to revert to other integration techniques. Finally, and this is where students often make mistakes, always perform a verification step. Before you apply the shortcut, explicitly check that the derivative of f of x is indeed equal to f prime of x. Double check that you've correctly identified f of x and calculated its derivative. This simple check will prevent you from applying the formula incorrectly and getting the wrong answer. Okay, let's recap everything we've covered regarding this special integral form. This is slide 9, and it's all about solidifying the key takeaways. So, to summarize, know the identity, understand its efficiency, be aware of the requirement, and always verify before applying. With these points in mind, you'll be able to confidently tackle integrals of this special form. Now, let's move on and practice applying this knowledge to more complex problems.